Okay, for our last example of how to do optimization problems as an introductory thing, we're going to do something that's actually pretty advanced, I think, and we're going to actually verify and develop Snell's law, which is from what rays and optics. This is actually problem, I think, 71 in the text. It comes with a picture, which is good. Basically, what it is about how light refracts or in water. Okay, so if you look at a fish in a fishbowl and it looks really big, but in reality it's not so big. Light just gets kind of messed up, and that's been interesting for ages. Anyway, we came up with some good stuff through the generations. Let's say that this is the surface of the water. So this is the water surface. And let's say you have some sort of light source over here, call it point A, and it is so many units high above the water surface, call it Y1. And say the light ray is shining and it's going to strike some point underwater, a different distance, call that point B maybe, and maybe that's Y2 below the surface. So the question is going to be, well, here's the story about this. This is what's really cool about it. It says basically the light will travel from point A, this goes in general, to point B in the least amount of time. In the least amount of time. Does that make sense? Maybe not. Who knew? Who even thought of that? But it's nature, isn't it? You fill up a balloon and it's not a cube, it's a sphere. Why? Because that's the least tension. Nature follows the path of least resistance. So when these light rays beam down, it's going to find some sort of point, let's call it here, and then go from there and bend. That looks pretty straight, so maybe I pick a different point, make it better picture, and maybe it's this point here to exaggerate. So the light is going to get to this point and then bend down to this point over here, and you'll see light bending. Pretty cool. Okay, so the least amount of time, right? And so the time it takes to go from point A to, you can call this anything you want, and then from that point on the surface down to point B under the water, we want to minimize the time it takes to travel. So that's the game. We're going to minimize the time the light wave, right, takes to travel from A to B. Okay, so hey, this actually boils down to some pretty simple stuff, because traveling from here to here, you have, let's call it T1. That's the time, okay? And then traveling here to here, let's call that like T2. All right, I'll move him out of the way for a good reason, and I'll put him underneath here. So that'll be T1 travel from there, and this will be T2, okay? What the heck? What do we need to know about traveling? Well, here's one thing that's going to help us a lot. This comes from, I don't know if you've heard of this before, but rate times time, of course I'm being silly, is equal to distance. Which means to us, time is equal to distance divided by rate. It would be fun for you to struggle over this. It's a good problem, but I'm not showing you the struggle here, and it would have been fun to watch me do it the first time. I go, now that I was going, the problem says do Snell's law, and he had angles in it. I went right for the angles, and that's not the best way to go. So I ran into a buzzsaw, and I go, that's not working. So I looked it up online, and I go, oh, that was my first idea, but I thought it was goofy. How do you get the signs in there? So what my first idea was, all we have to do really is, well, let's just let's call this distance from here to here x. Now x is mobile. It's variable. X could be here, X could be here, I don't know where, anywhere you want X to be, okay? So X is the guy that's going to be kind of changing on us. But once you have X established, you can figure out what this is, maybe call it D1. You can figure out what this is D2. And oh, by the way, I forgot to tell you, This is also a fixed distance from, say, here to here. I called it D, like capital D. How far apart is A and B horizontally? Call it D. So that allows us over here to write this as D minus X, if that makes sense. So stare at that picture, pause it, okay, and then when you're ready, keep moving. This video, I'm going to keep talking, but hopefully you paused it and took a look. So here's the thing, okay? Forgot one other thing. The speed of light in air versus water is different. That's what makes this whole thing happen. If the speed of light was always the same no matter what the medium, then we wouldn't have infraction. We wouldn't have those weird things with the fish in the fishbowl. It would just be straight through, okay? But apparently, light slows down in heavier media. It's like the speed of light in vacuum, and then you have the speed of light in air. Did you know that the light actually bends at sunset? It bends due to the pull of gravity. Light does a lot of different things. It hits our atmosphere and bends, okay? Because it slows down for some reason. Interesting stuff. Anyway, we'll say this also. The speed of light in air is like, call it just V1, and you can use any unit you want. And the speed of light in water is V2. This is just a cool example to show you how deep this can go with your derivative. So here's the thing. We want to minimize time. I'm going to start using letters. Let T stand for time. And I'm going to jump to this. I'm just going to say, and it depends on where you place X. If it's really close or far away from A, it depends on X. Because look, we're going to say it's equal to T1 plus T2, okay? But that's equal to, you ready? D1 divided by V1, distance divided by speed, plus D2 divided by V2, distance divided by speed. So we got a lot of things going on. We got the speed changing, and we've got X could change. It depends on where you want to place it. But nature's going to place it to where, at a location where you have minimal time. Okay, let's do the problem. One more step. Did you notice that we have right triangles in here? Isn't that cute? So here comes some old guy named Pythagoras to also help us. So for example, we could say D1 is the hypotenuse of this triangle here. And it's equal to the square root of y1 squared plus x squared, whatever x is, right? Likewise, D2 is the square root of y2 squared plus, his side is weird, it's d minus x quantity squared, like so. Folks, we are there, but that was a tough one, wasn't it? A lot of stuff going on, a lot of knowledge. By the time you get here in physics, you'd be through physics 1 and 2 probably, and you're just so used to it, and you go, yeah, I understand why that's happening. Interesting to see how light waves change. It's all depending on the light waves and going through apertures and, you know, between atoms and whatever, I imagine. It's been a long time for me. But anyway, T of X is, I'll replace D1 with this radical. So we get this over this, right? Plus this guy, right? D minus X quantity squared over this guy. And this guy we want to minimize. Each one of our problems is minimized. Oh, well, no max in my videos today, or in this section. Have to go to class to see them, I guess. But to minimize, you know what we're going to do? T prime. Why? Critical points. That's why. We want to find the critical numbers. Okay? So we take the derivative. It's really not as bad as it looks. I'm going to move the 1 over V1 out. You notice the constants here? What are the constants in this equation? Everybody's a constant except for X. Really? Yeah. What's Y1 stand for? How high is point A? What does Y2 stand for? How deep is point B? Those are fixed numbers. Okay? They are. You just, whatever you want it to be. What is V1? Oh, that's the speed of light in air. It's fixed. Pretend. What's the V2? Speed of light in water. Okay. What about capital D? Oh, that's a fixed distance between A and B. Well, then what is moving? X. X can be anywhere from 0, which means he's right under A, to D, means he's right over B, or anything in between. So that's the guy that's changing, and he's going to be forced to be something to minimize. So that's what we're doing. we're going to derive with respect to x. And so now I'm looking at a radical. I have that memorized. It's like 1 over 2 square root, this guy. But the chain rule says now derive the inside. And the inside derived is 2x. Because y1 squared is just a constant. For the next one, same thing. I'll move the v2 out of the way. Why do I do that? Because I'm experienced. I know what to do. This is 1 over 2 square root y2 squared plus d minus x. Different kind of derivative this time. And how does it derive? How do you derive that thing? y2 squared is 0. It's a constant. But I'm going to use a chain rule on this and go times 2 d minus x to the 1. And then the derivative inside is -1. All of that. So t prime, we're almost done actually. It seems like we're going forever. Looks like the following. First, I'll cancel those 2's. I'll cancel those 2's. Okay, done. And I'm going to write it as, let's see. How do I want to do this? Oh, yeah. I want to write it as 1 over v1 times x over the square root y1 squared plus x squared. I'll bring the minus in front of this other guy, 1 over v2, and then times, looks like what we've got here is a d minus x all over the square root of y2 squared plus etc., d minus x squared, okay? That's our derivative. And that thing we set equal to 0. But wait, hold on. Here comes Snell's little cute thing. You ready for this? This is insane. We have to cruise back up here. And one guy I did not invite to the party until now is the following. They have 2 angles here. So he's going to translate this into angles, okay? So right now we're pretty good. We can figure this out. But he's just going to, instead of doing this, he's going to say one more party crasher is theta 1 is the angle, what they call the angle of incidence, I think, of the light hitting, and that's really hard to read, so let's try that again. So I will, I'll bring it down here. So theta 1 is the angle of incidence of the light. When it hits the water, it's at a certain angle. And theta 2 equals the angle of refraction. I believe those words are right. It's from the textbook. You can find that thing. Anyway, what's weird is, look at this. X over the radical, d minus x over its own radical. Look at the diagram up here. If theta is up here, x over this guy, radical, is actually opposite over hypotenuse. Same story here. Opposite over hypotenuse. That should be a minus. That looked like an equals. Over this hypotenuse. That's the ending of this problem. It went kind of fast, I'm afraid, when I did that. But what we'll say is that, there we go. That's not what I want. I don't want that. Okay. Is the following. So t prime of x is really 1 over v1 times sine theta 1 minus 1 over v2 times sine theta 2. I'm sure your physics teacher can do better than I did. And the critical point happens when this is 0. And here comes Snell's law about light hitting a surface and changing speed. The sine of the incidence of the light ray divided by the speed of light in air is equal to the sine of the angle of refraction divided by the speed of light in that other medium. And that problem is done. That's what they wanted us to show. And it's a lot of work. I gave you one that's got a ladder going around a corner. That's another good one. Although Snell's law, I mean, come on, we just did some physics. So it's good to see it. I know there's a lot to kind of absorb there. I could have done a better job of it to put all the pieces together, but it's done. So enjoy that one. And we're going to move on to the last 2 sections with our videos. See ya.